Katie here. This is the first lecture of the Marine Atmosphere module, and we're going to start off by talking about the importance of NOx, in particular the variations in polluted and remote marine atmospheres, and of course where those mix in the coastal environment. So first, to start, what is NOx? A bit of a review here from Atmospheric Sciences. NOx is not a real thing in and of itself. It is the sum of NO and NO2, and it's a chemical family. Other chemical families include HOX and CLOX. Might get into those a little bit later. But essentially, NO and NO2 are two species that cycle extremely rapidly, less than a minute during the day, even faster with the latent relationship. And you can see the chemistry here. This figure on the right shows NO and NO2 as it fits in with ozone and HOX chemistry, and that's going to become a little bit useful later. But essentially, NO is oxidized to NO2 in two different forms, only one of which is shown on the right. Equation 10 is the oxidation of NO with HO2, and that forms NO2 and OH. An alternative option is the oxidation of NO with ozone, which leads to NO2 and O2. Then as soon as NO is oxidized to NO2, NO2 is then very rapidly photolysed back to NO in a process that requires light in the presence of oxygen, which there's plenty of in the atmosphere, and it forms NO and ozone. And so this essentially happens constantly, back and forth, back and forth, back and forth, back and forth, until it's almost impossible to measure them separately. Not impossible, but very difficult. And so it's much easier to refer to it as a chemical family in that sense. Of course, because the oxidation or the reduction of NO2 to NO requires light, it means that at night that can't happen. So at night, you keep forming NO2 through the NO plus HO2 and NO plus ozone pathways, more so through the NO plus ozone pathway. But then you can't break the NO2 back down to NO. And so NOx at night is essentially equivalent to NO2. So why is NOx important? There's three main reasons. The first is that NOx is responsible for boosting the oxidizing power of the atmosphere. So the atmosphere is a very oxidizing place. And the main oxidant that sort of oxidizes pretty much all of the gases in the atmosphere, and as a result is a main control on the chemical composition of the atmosphere, is the OH radical. You can see it down here in this place. So NOx cycling, if you think of the sum of 10 and 11, so these two reactions here, so NO releases HO2, or NO and HO2 form NO2 plus OH, NO2 then decomposes to NO and ozone. That ozone then goes on in reactions R1 through 3 with light to form water. Water then, this is water vapor, forms two H molecules. So the cycling of NOx in net, if you look at reactions 10 and 11 and 1 through 3 here, actually produce three OH molecules. So two OH molecules here and one here. And so this is a really big source of the OH molecule in the atmosphere, which is the main oxidant, and the troposphere is an oxidizing place. So understanding NOx sources and sinks and the ability of NOx to stay in this cycle here and not be removed is really important for understanding OH concentrations and the oxidizing power of the atmosphere. The second thing about NOx that's really important, and this is more in happens more in polluted environments, but it also does happen in remote environments, is the formation of ozone. And so here I've added two more equations. So you have reaction 10 and 11, which we've already talked about. So NO oxidizing to NO2 and then being photolysed back to NO. But CO, carbon monoxide, which is one of the main natural VOCs, reacts with OH to form CO2 and H2. And then you have this reaction where the H2 reforms with O2 to form HO2. And there's a whole bunch of reactions here that I'm not including, but let's suffice it to say that the oxidation of CO by O2 is catalyzed by the HOX and NOx families, and you end up with the production of ozone as a net response here. Ozone is a greenhouse gas, and I'm specifically referring to the troposphere. And so ozone is a pollutant, leads to smog, but also a greenhouse gas. So NOx, again, is really critical in setting the production of ozone. The third thing is that when NOx is removed from the NOx cycle, you can think of it, or oxidized away, but essentially the fate of, NOx just doesn't keep cycling. It is eventually converted to something else. That something else is nitric acid and aerosol nitrate. And so nitric acid and aerosol nitrate then play a really important role in the aerosol composition of the atmosphere, in terms of, so then they're impacting the scattering and absorbing of solar radiation. And that aerosol nitrate and nitric acid also can play a role in wet and dry deposition. So the nitric acid contributes to the acidification. So if you're thinking about things like acid rain, and then the aerosol nitrate and nitric acid also contribute to nitrogen deposition to ecosystems. And so the loss of NOx varies during the day and at night. This sort of cartoon schematic here shows the daytime where the yellow background is on this side here, and then the nighttime is where this sort of dark gray background is. And I think this is quite nice because it shows sort of in a cartoon way the cycling of NO and NO2 with ozone and light, and then how you lose the loss processes of NOx. So during the daytime, you lose NOx through the reaction of NO2 with OH. And again, like I said, OH is the oxidant, sort of oxidizes everything. And that's this reaction here, NO2 and OH forms HNO3. This M you'll see throughout a lot of atmospheric chemistry reactions. It just means that some inert body is needed. It's neither produced nor consumed, but it's, you can essentially, I guess, ignore it. But it's there for completion to be accurate in terms of what type of chemical reaction it is. So you have NO2 reacts with the OH to form HNO3. HNO3 is then quickly hydrolyzed. You can see it goes this way with rain, and then deposited as wet and dry deposition. At nighttime, there's very little OH molecule at night. If we go back, oh no, I don't have it here, sorry, okay. If you look here on this reaction, the production of OH from ozone and water requires light, and then OH is destroyed very quickly without light. Not destroyed, sorry. OH is not reformed at night because there's no light, and so this pathway of NO2 reacting with OH can't happen at night, and so something else has to happen. And there's a couple of options in this case. NO2 can react with ozone to form the nitrate radical. And since there's no OH around, the nitrate radical is the main nighttime oxidant. There's three main oxidants, OH and ozone and the nitrate radical. So NO2 reacts with ozone to form the nitrate radical at night. And again, this is an example where NOx is now setting the nighttime oxidant budget. The other thing that happens is once you have the nitrate radical present, it reacts with NO2 to form this N2O5 species. N2O5 is a gas that then combines with atmospheric water to form nitric acid, aqueous nitric acid. And so again, you end up with NOx converting to nitric acid, but through a very different chemical mechanism at night than it does during the day. There's a couple of other more complications here. In this diagram, it shows very nicely how ammonia gas reacts with nitric acid to form ammonium nitrate. That's another type of nitrate aerosol. And this diagram also shows nicely how trees and other industrial processes lead to VOCs, which are another way in addition to HO2. That's where this RO2 comes in, that you can oxidize NO to NO2. Okay, so that's the sort of loss processes. And then, of course, the fate of NOx ultimately is to become nitrates. And when we get to the lecture on the sulfur nitrate ammonium system and the lecture on aerosols, we'll talk a little bit more about the fate of this aerosol nitrate. So where does NOx come from? Globally, it's thought that the largest source of NOx is from fossil fuel combustion, industrial activities, vehicles, etc. The next largest source is a natural source from lightning. You can see that in this diagram here. So lightning strikes have such high energy that the N2 gas in the atmosphere is actually oxidized from that process, and so it leads to NO formation. There's also NOx from biomass burning, and that can come from high temperature combustion of the N2, but it also can come from the burning of actual organic nitrogen in the plant material. Soils release NOx, both managed soils and natural soils. There's a minor source from the stratosphere. Biofuels here are listed out on their own, and then aircraft NOx. Of course, this varies country to country, and when we're talking about NOx emissions from a pollutant sense, we frequently bin them by country, so that because the ability to reduce NOx emissions is a policy-driven process, and so that can only be done within national borders. And each country's NOx emissions look slightly different. You can see this is an old NOx budget for the US, where transportation was the largest contributing factor. If we look at South African NOx emissions, it's primarily driven by the fact that electricity production comes from coal, and so that's your largest driver of NOx emissions in South Africa, and you can see that spatially as well. On the top, this is a satellite view of NOx emissions across South Africa, and you can see it overlaps very nicely with where the coal-fired power stations are. And you guys should have seen this image on the left before. These dark spots are where your highest NOx emissions are, and they overlap very nicely with the blue circles, which are the physical locations of power plants. This is an image from the Tropomi satellite. So NOx emissions are understood in two ways, the first being bottom-up emissions inventories, and that's what is shown here on the top. So that's where you say, we know we have these various sources, we know what their activities are, and we use some emissions factor, and we calculate how much NOx emissions there should be. The other way is looking at the more top-down approach where because NO2 is spectroscopically active, we can use satellites to measure the total column concentration, the total column meaning not just at the surface, but the concentration throughout the atmosphere. And this is a pretty typical NO2 column approach where you can see the really dark values in Europe and in Asia. This would be from burning here, and then this is the Highveld. You can also see really nicely shipping lanes where you've got these enhanced NOx emissions from ships burning really dirty diesel fuel. You can also see biomass burning regions. You can see most of the major cities in the world. And you can also see that for the most part, NOx concentrations are quite low over the remote open ocean. So when you think about differing parts of the atmosphere, there's very different NOx sources. So it's not really useful to think of a global NOx budget because in any given region of the atmosphere, of course, it's not going to be influenced by the global budget. It's going to be influenced by more regional scale because NOx is not a greenhouse gas in the sense that it's super long-lived. The way something, like CO2 emissions are really long-lived, and so they mix really evenly around the atmosphere. That's not true for NOx. Regional sources are more important in terms of local chemistry. So in a polluted atmosphere, somewhere like the city of Cape Town or in the Highvelds, you're going to have primarily NOx from fossil fuels, so from combustion, industry, and vehicles. You might have some biomass burning. This can also include domestic burning, so burning for heat. You're going to have NOx from soils, both natural and managed, meaning from fertilizer added to soils and then just from regular soils. You're always going to have a lightning signal, although that does vary latitudinally, and it's actually quite high at mid-latitudes. you're going to have a very minor aircraft and stratospheric input. The stratospheric input will also vary latitudinally and seasonally. We're not going to worry too much about stratospheric inputs. They're pretty mild. So if you think about the remote marine atmosphere, depending, of course, on where you are, your main source then is probably going to be lightning. As a remote source, you'll have maybe a little bit of aircraft and stratospheric input, depending on where you are and what the season is. You have to worry about long-range transport. So there are, and I'll talk about that in a moment, the ways that this polluted NOx can make its way out to the remote atmosphere. There's also in recent years been a focus on the potential for surface ocean emissions, and that's really interesting. In fact, Jess, your tutor, is working on surface ocean NOx emissions, surface ocean emissions that lead to NOx formation in the remote marine atmosphere. And then if you're remote in the sense that you're in the Arctic or the Antarctic, you have to keep in mind photochemistry on ice. And so nitrate, or nitric acid that's in snow, can be photolyzed and re-emit NOx to the Arctic and Antarctic atmosphere. So in terms of remote ocean NOx sources on the left, this shows you there are these molecules that are called reservoir molecules. And so what ends up happening is in a polluted region where you have high concentrations of NOx and high concentrations of certain organic molecules, you can form PAN, which is called peroxyacetyl nitrate. It's an organic nitrate molecule. And if you have vertical mixing in the atmosphere, and you can get that PAN up to where temperatures are fairly low, it becomes very stable. And so then, because it's stable and it's in the upper troposphere, it can be transported fairly long distances. And so it can go along all over the atmosphere. And then if that air mass subsides somewhere where it's relatively warm, that PAN will thermally decompose and lead to NOx formation, and then that NOx will be converted to nitric acid and then potentially deposited in the remote atmosphere, even though you're super far away from where this NOx was actually emitted. So PAN is a key sort of long-range transport molecule. The other thing, and so that would be, this is a schematic from a fairly recent review paper about ocean-atmosphere nitrogen cycling. And so this PAN would be identified, it would fall in this arrow of long-range transport of transported in nitrate or transported in NOx. And you can see on the right-hand side here, this dissolved organic nitrogen in the ocean leading to organic nitrogen emissions. These are alkyl nitrate emissions. And those organic nitrate gases can be photolyzed to form NOx, which then leads to nitric acid and nitrate aerosols. And this is that fairly recent ocean process that I was just talking about. So the other thing, of course, is the presence of ice. And this is a cool schematic from the Ketch paper. Recently, Ketch is the Cryosphere Atmosphere Organization. And it's kind of a neat way to look at the scale of Antarctic ice and Arctic and Northern Hemisphere ice as compared to land mass and ocean cover. And so ice frequently impacts atmospheric chemistry in these marine environments, especially in regions where you have mixtures of open ocean, sea ice, pack ice, etc. You can have a combination of things happening. And so the NOx comes from chemical exchanges in the snow and these microscale processes where you have sunlight coming down and then NOx coming up and interaction of these molecules. You also can then have NOx reforming nitric acid, which is then deposited back on ice and snow. And if you are in a region where you have things like shipping, which is more in the Arctic than in the Antarctic, you can have a mixing of these photochemical NOx sources, the natural NOx sources, and then your anthropogenic shipping emissions. Of course, another thing to keep in mind, we're sort of, when I was talking about polluted atmospheres versus remote atmospheres, I was treating them as if they're similar, but the relative concentrations vary a lot. So this is kind of a cool model figure. It shows NOI here. Don't freak out. I know NOx, NOI, CLOX, CLOI, it gets a little bit crazy. NOI is NOx plus nitric acid, pan, and aerosol nitrate. So it's all those species together. And if you look at the northern hemisphere on the right-hand side, this is latitude and degrees north here, the values for NOI go up to 350 ppt, whereas on the left-hand panel, we've got the southern hemisphere and the tropics, and those values go up to 100. And if you just look at NOx, which is the blue, you can see NOx concentrations peak in your mid-latitude northern hemisphere, as you might expect from human activities, at around 75 ppt. Whereas NOI in the southern hemisphere, if you look from, let's say, 20 south on down to Antarctica, your maximum concentrations here are about 10 to 15 ppt, and that's parts per trillion. So we're talking in the remote marine environment or in the cleaner atmosphere, there's a lot less of everything. And then, of course, your chemistry is different because there's not just a lot less NOx, there's less oxidants, things like OH and ozone. And so your relative distribution of nitric acid in green is very different. You can see pan as one way to penetrate the remote marine atmosphere, and then your formation of aerosol nitrates, and then and this paper was focused on alkyl nitrates, and that's what you're showing here in the yellow. So this is a model estimate of what the contribution of alkyl nitrates should be, and you can see it's huge. And this is really interesting and exciting research that's currently happening. And then, of course, the contribution of those alkyl nitrates is much lower in the northern hemisphere system. Okay, so that's that. And then this is another way of looking at the relative concentration. So now you're looking vertically in the atmosphere and across various latitudes using these isopleths of concentration. And here again, this is NOx concentrations in ppt on this first diagram. And you can see they're very high at the surface in the mid-northern hemisphere, declining up in concentration, and also declining as you move into the southern hemisphere. Similarly, you can see ozone concentrations where they're peaking, and then your CO and OH concentrations. So NOx in and of itself is lower in concentration in these clean atmospheres as compared to the more polluted atmospheres, but also NOx is influencing these other oxidants, and its chemistry is being influenced by the oxidants. So it's all a bit complicated and intermixed. As a result, there's a lot of open questions and key issues around NOx in terms of the role it's playing in the atmosphere. Everyone sort of felt pretty confident that anthropogenic NOx emissions dominated everywhere until this Nature Communications paper came out a couple weeks ago that talked about the summing up the relative importance of non-fossil fuel related NOx emissions globally, actually using stable isotopes, which is a tool we use in our lab as well, suggesting that we have underestimated the importance of natural NOx emissions, which is not surprising. It's very difficult to measure natural unperturbed systems. So the other thing that's an open question and a key issue is the role of the surface ocean. So when you get far away from land, the assumption was that you would have lightning and long-range transport of anthropogenic emissions. But that modeling paper, the slide I just showed you, suggests that that's not true. And in fact, our measurements and measurements from some other groups suggest that that's not true, that the surface ocean is definitely playing a role. And then the other open question is about pre-industrial NOx cycling and oxidation. And again, this gets to the issue of it's very difficult to find a place in the atmosphere that's comparable to the pre-industrial, where we don't have some influence of anthropogenic NOx and anthropogenic oxidants. And this is a problem for our ability to predict things like nitrate concentrations and aerosol nitrate concentrations, which of course feed very heavily into our ability to predict climate into the future because of our inability to understand climate and the interactions of this chemistry in the past. So that brings me to, the last slide here. Again, just coming back to a lot of the lectures this week are going to touch in some way on the nitrogen cycle because it's my personal favorite, but also because of the important role. This figure doesn't really show it, but that NOx touches on all aspects of atmospheric chemistry in terms of oxidation, in terms of the oxidizing power of the atmosphere and the formation of ozone and polluted environments, but also the oxidizing power in remote environments and the formation of aerosols and their climate impacts in remote environments. So that's it for NOx.